everyone. Welcome to the first lecture on curves and surfaces. So in this lecture, we'll be defining what you mean by a curve. So a curve is a smooth one-dimensional object sitting inside a space. So in order to define a curve formally, we need some basic terminologies in mathematics. So let us begin with those basic terminologies. So first, let me define this n-dimensional real space, or let me write real n-dimensional space. Okay. So we start with R, so it is the set of real numbers. And so what is my n-dimensional space? So this is my Rn. So this is defined to be this x1, x2, xn order tuple, and where this all this x1, x1, xn, it belongs to the real number set. Okay, so I have now defined the space, and so this Rn, so it is a vector space over R. So what is the addition on this Rn? So this is defined to be, so if I take any 2 points, so the addition is just component wise. And then you have the scalar multiplication. So scalar multiplication on Rn. So what is that? So if I take any lambda, which is a real number, so lambda dot this x1, xn, so it is, so the scalar multiplication, it is defined to be lambda x1, lambda xn. So this is the definition of scalar multiplication. And with respect to this addition and scalar multiplication, this Rn, it forms a vector space over R. Okay. So now we have a nice algebraic structure on this Rn, and now we define a distance function on Rn, so which is called your Euclidean distance. So let us take 2 points. So let x equals to x1, xn in Rn, and let us take another point y1, yn in Rn. So both of these elements are in Rn. And what is the meaning of this Euclidean distance? Between x and y. So this is defined to be the root over summation I equals to 1 to n xi minus yi whole square. So this gives you the distance between x and y. So this xi, y, so these are vectors in Rn. Okay. And also we have the concept of norm here. So let us take any element x in Rn. So norm of x, so which is denoted by this symbol. So this is defined to be uh, root over x1 square plus up to xn square. Okay, all right. Okay, so now, so we'll be defining curve. So in order to define that thing, so first let me define what you mean by uh, continuity of a uh, map from an interval to your Rn. Okay, so first let us recall, so what is the definition of a real valued function which is continuous? So let us take a, so let f I to R be a real valued function, be a function. So where this I is an interval. So where this I is an interval. So this I, it may be closed interval like this, or it can be semi-closed like this, or it can be also maybe unbounded interval, something like this. Yeah. So now let me define, so what do you mean by continuity of this f? So let us take, so let x0, it belongs to the interval I. So f is said to be continuous. So f is said to be continuous at x naught. So if for all epsilon greater than 0, so there exists delta greater than 0, such that uh, so this norm of, or maybe I'll just write, so mod of fx minus fx naught is less than epsilon. So whenever uh, mod of x minus x naught is less than delta. Okay. Yeah. So this is the definition of continuity. So whenever you have mod of x minus x naught is less than delta, so then mod of fx minus fx naught is less than epsilon. Okay. So now the same definition. So if I take the function, so let us take, so this function, so let f, now it is a function from this interval to your Rn. So f is said to be continuous at x naught belonging to I. So if again for all epsilon greater than 0, so there exists delta greater than 0, such that now in place of mod, you replace it by norm. Norm of this fx minus fx naught, which is less than epsilon whenever mod of x minus x naught is less than delta. Okay. So this is the definition of continuity of f. Okay. So now, so let me define a curve. So what do you mean by curve? Okay, so again, before defining curve, so let me state this thing. So suppose you have a map from this f from I to Rn. So this f you can write like this. So ft is equal to f1t, fnt. So this f1, fn are the component functions of this f. So f continuous at t naught if and only if. So each of this fi I equals to 1 to n is continuous at t naught. Okay. So now let me define. So what do you mean by a parameterized curve? So a parameterized curve alpha in Rn is just a continuous map, is a continuous map alpha from an interval I to your Rn. Okay. So where this I is an interval in R. Okay. The so the image of alpha, or let us take or alpha I, which is in fact the image of alpha in Rn, is called the trace of alpha. Okay. And if I take any t belongs to I, so t belongs to I is called the parameter of the curve alpha. Okay, so let us give some example. So let us take, so this alpha t to be equal to your cos t sin t. So t is varying in this interval 0 to 2 pi. So this image of alpha or trace of alpha, it is just unit circle with center at origin. So if I take t equals to 0, it starts from here. Yeah. So and if I take any t, so this alpha t is cos t comma sin t. So this image of alpha or trace of alpha, it lies in R2. So therefore this alpha, it is a planar curve. Okay. So let me give you another example. So alpha t is t comma mod of t. So t, it is varying in this interval minus infinity to infinity, which is just r. So the image of alpha or trace of alpha, it is this graph of mod x. Yeah. Okay. So again, image of alpha in this case also, it lies uh, in in R2. So therefore, this alpha, it is a planar curve. Okay. And so third, so let me give you this example, alpha t, so which is your cos t sin t comma t. So now the image of alpha, it lies in R3. So it is no longer a planar curve. Okay. So what will be the trace of this alpha? So I can draw it here. So let us take this three-dimensional space. And so this image of alpha, it lies on the cylinder. So let me draw the cylinder first. Okay, now let us draw the curve. So if I take, so this t equals to 0. So if I take t equals to 0, alpha of 0 is 1 comma 0 comma 0. So if this is my x-axis, this is my y-axis, and this is my z-axis. So the curve, it starts from here. So this is my 1 comma 0 comma 0. So this curve, it starts from here, and it will be something like this. It will be spiraling around the cylinder. Yeah. So the image of alpha, it is a spiral. Okay. So this image of alpha, it also lies in R3. Okay. So in the first example, so this curve alpha, so it is a planar curve. So here, if I take any point here, this alpha t, if it is alpha t, it is equal to your cos t sin t. Okay. So note that in this first example, so this cos t and sin t, so these are my differentiable function. So therefore, this curve alpha t, it is differentiable. But in the second example, so if I take this function t goes to mod t, so it is a continuous function, but it is not differentiable at t equals to 0. So therefore, this curve alpha, it is not differentiable at t equals to 0. So in this course, so mostly we'll be dealing with differentiable curve. So let me first define, so what do you mean by differentiability? So let us recall few things. So differentiable function. So let us take an open interval. So let I be an open interval. So a function is differentiable at a point x0 belongs to I. So a function f, so f is a real valued function, is differentiable at x0 belonging to I. So if the following limit exists, so if, so limit x tends to x0, fx minus fx0 divided by x minus x0 exists. Okay, so then we say that the function is differentiable at x0. And so if it exists, so then we write, so this limit x tends to x0, fx minus fx0 divided by x minus x0 to be your f prime x0. This is the usual notation we do. Okay. And now we say a curve is differentiable. So let me write differentiable curve. So a curve alpha I to Rn, where this I, now it is an open interval, is differentiable so if so this limit, if limit alpha t minus alpha t naught divided by t minus t naught, so this limit, it exists for all t naught belonging to this I. So if this limit exists, so we say that this alpha is differentiable at t naught. Okay. Uh, so so this, note that this alpha, so the image of alpha, it lies in Rn. So I can write, so this alpha t as alpha 1t, alpha n t. So now if I take this difference, alpha t minus alpha t naught, so this is an element in Rn. So I can take 1 by t minus t naught. So this is a scalar. So here I am doing this scalar multiplication. So this will be equal to your alpha 1 t minus alpha 1 t naught divided by t minus t naught. Okay. So this identity tells that, oops, sorry. Yeah, so this identity, it tells that, so if I take, so if I take limit t tends to 0, Okay, so if I take this thing, if alpha is differentiable, so each of this alpha I is also differentiable. So alpha prime T naught is equal to your alpha 1 prime T naught dot alpha n prime T naught. Okay. So what is this alpha prime T naught? So this is limit t tends to T naught alpha t minus alpha T naught divided by T minus T naught. Okay. So alpha differentiable at T naught, so implies alpha I is differentiable at T naught for all I equals to 1 to n. And the converse is also true from this identity. So from this identity, the converse is also true. Okay. So therefore, so in this lecture, so we have learned about uh, differentiability of a curve. And also let me use some, I'll be using some notation. So let me tell that thing to you. So alpha prime T naught, so this is the derivative of alpha at T naught. So this also we write like this. So notation. So sometimes I'll be using this notation also. So alpha dot T naught is just equal to your alpha prime T naught. Okay, so I'll stop here. So in the next lecture, we'll be defining length of a curve.